This video is on the ideal gas law. This video is only for IB chemistry. So the ideal gas law is essentially just a formula. It's a formula to calculate 4 different variables. So pressure, volume, temperature, and moles, just at a certain set of conditions. At a specific set of conditions, meaning there's no change. So what is an ideal gas actually? So you can write this over on the side. So an ideal gas is any gas that fits the kinetic, molecular theory at all temperatures and pressures. And the kinetic molecular theory just explains gases and their behaviors. So this just ideal gases are ones that do everything it says in that theory. The thing is, in the real world, we actually have real gases. So real gases only fit, and I'm going to abbreviate kinetic molecular theory, at high temperatures and low pressures. So high temps and low pressures are when real gases will act like ideal gases. The thing that we're going to worry about, though, is just we're going to assume that all of our real gases are actually like ideal gases. So we're going to treat all real gases like ideal gases. So even though they technically don't fit all of those behavior descriptions in the kinetic molecular theory, we will assume that they do for the most part. So back to the formula. The formula, I'm going to write that in as the equation part here first. The formula, the equation is, if you take the pressure and you multiply times the volume of any gas, you will always get the same as the moles times R, which is going to be our constant, times the temperature. So pressure, volume, moles, and temperature are up in the definition in green. Those are variables. R is a constant. So the value for R is 8.31. And this is given in the IB data booklet. So you don't necessarily have to memorize this. However, you probably will just by using it over and over again. The units are a joule per mole Kelvin. So if you remember, IB prefers to write units in the denominator with the negative subscript. So this is the same as saying 8.31 joules per mole Kelvin. Right? Same thing. Okay? So this is that constant R. So in any given problem, you're going to be given all the variables except for one. So your job is to use the equation to solve for the missing variable. It's just like in math when you solve for x. So we just have to know what the variables are and what their units have to be. There are very specific units for each variable. So P stands for pressure. And pressure needs to be in kilopascals. Okay, so that's why in the last video you learned how to convert from different pressure units. V is volume, and volume must be in liters, which is decimeters cubed. Technically, kilopascals and decimeters cubed cancel each other out. The correct, I suppose, right, I don't know, units for them are pascals and meters cubed. But we're going to see liters or decimeters cubed and kilopascals more often, and they will cancel each other out, that change from pascals to kilopascals and meters cubed to decimeters cubed. So these are the units you need to worry about. The moles are N, and they are essentially already a unit. And temperature for T needs to be in Kelvin. So that's why in the last video you learned how to convert Celsius to Kelvin, right? Adding 273 will give you 2 Kelvin from Celsius. All right, so let's do an example problem. So it says calculate the volume of 0.0250 moles of nitrogen at 35 degrees Celsius and 780 millimeters of mercury. So list out your variables. This will help you get started. So calculate the volume. So that means V is my unknown. And my moles, so N equals 0.0250. 35 degrees Celsius, so that's my temperature. Remember to keep all sig digs. That won't matter. And pressure, 780 millimeters of mercury. Alright, so first thing I'm going to do before I even get to my equation is I'm going to check my units. Okay, volume will end up being in decimeters cubed, which is fine. It didn't specify a certain volume unit. Moles is moles, yep. Temperature, okay, I have to convert that to Kelvin, so I'm going to add 273. So that will give me 308 Kelvin. And we're going to keep the same numbers after the decimal because we're adding. So 308.0 Kelvin. And my pressure, I have to do the quick unit conversion. So there are 760 millimeters of mercury and 100 kilopascals. So millimeters of mercury divide out. So typing this in my calculator, I get 103 kPa. I'm going to have 3 sig digs. Alright, now that I have all my variables, except for one, correct units, I can go to my equation. So, PV equals nRT. Solving for V, that's my unknown, I need to get volume by itself. So on both sides, I'm going to divide by pressure. So it will divide out on the left side. So my equation is moles times R times temperature, all divided by pressure. So I plug in, I'm actually going to move this over a little bit. Okay, I'm going to plug in all my numbers now. So N is 0.0250 moles. My R is 8.31 joules per mole Kelvin. My temperature is 308.0 Kelvin. All of this divided by my pressure of 103 kPa. So unit-wise, you can see that moles divide out, and you can see that Kelvin divides out, and a joule has a Pascal in it, so that part will cancel, and you will be left with your decimeters cubed. Because you can think of your joule unit, this unit, another way of writing it, would be a kPa times a decimeter cubed instead of joule over a mole times Kelvin. Okay, so that's a way to write it so you can see that your units divide out. So when I type this in my calculator, I get 0.621 decimeters cubed for my volume of this gas. The practice problem you also see on your paper we'll do in class together.